Focus during this project was to experiment efficient materials and strategies to travel to Mars. To do so, we used a circuit conduction experiment and found the estimated amount of energy needed/used to launch our quote-unquote rocket. To plan our experiments, we all individually brainstormed how our science related to the given topic. From there, we discussed our options and what would be realistic but still successful in a small-scale experiment. This resulted in our plan to find a suitable conductor for the electricity needed to power a rocket using a circuit set and find the energy used/conserved based on a metal rocket.
Hello, I'm going to be discussing the biological aspects of going on a mission to Mars. So for our project, we did a little simulation where we did a rocket ship which essentially plummeted into Earth. So of course, throughout this project, we couldn't use a human to analyze the biological effects of preparing our bodies for a mission on Mars. So I'll be discussing it because if we did use a human, that could have been very hazardous and could potentially put somebody in great danger, obviously. So when our bodies are plummeted into outer space in order to go into Mars, our body will react very negatively just because we as humans are used to the conditions on Earth and not in space. Because in space, gravity is very weak, so our bodies will be in a very fragile state where our bones and muscles are bound to weaken, our endurance decreases, and we lose our density. So that's what happens while on space. However, when we do arrive at Mars, which is usually a duration about 7 months, which is quite a long time, it definitely does not get any easier because in Mars, there's a bunch of radiation and it's extremely high, very dangerous. You have to be very well equipped because it can be very hazardous and will kill you if you are not taking care of yourself. So to protect yourself on Mars, you need to build an environment that can keep you in healthy conditions, like an igloo, or you can build somewhere underground in order to protect you from the radiation, which is deadly. You also need to wear a spacesuit, of course, and have a large supply of oxygen to be stabilized throughout your journey on Mars. If you do this, well, you'll be able to live in Mars, but in order for Mars to be habitable for humans, you must also, as again stated, have oxygen, a renewable supply of oxygen, to keep using over and over again. You must have water, power, and food to survive the Martian environment and be biologically at a healthy state. If you do this, you're going to find yourself being able to live Mars well, but if you don't, you're going to die, so be careful. Bye.
Hi, my name is Domarie, and how the use of biology is being observed in the second experiment, which is called a baking soda rocket, and how we thought of it was demonstrating on how our bodies would react to being in Mars, and how biology is being observed through the understanding of chemical reactions and how they can be related to biological processes. And for the experiment how the experiment would be demonstrated for our bodies. It would react to being on Mars by producing more carbon dioxide due to the lack of oxygen, similar to the reaction of baking soda with vinegar.
Hi, I'm Quinn, and my two sciences were chemistry and SEHS. Chemistry was used in both experiments. For the first experiment, we decided to use a little circuit kit to run an electrical current through different materials to see which ones would be best at connecting energy through a rocket when we're blasting off. From this, we learned that metals like aluminum, steel, gold, and copper were really good conductors, but things like wood, rubber, paper, and cloth were very poor conductors and would be better off used inside the rocket where we don't want any electrical connections. We also found out that specifically salt water was a really good conductor, which is interesting because regular water isn't, and we found out it's because of the ions in sodium chloride, the salt. For experiment 2, I used my knowledge of chemical reactions, and we made a reaction between vinegar and baking soda, which produced CO2 and built up enough pressure to actually launch our bottle rocket. For SEHS, again, as previously mentioned, biological experiments aren't really realistic to test in such a short amount of time. However, we kept in mind how long it would take to travel to Mars based on our estimated required force and energy production that we found out using our physics principles. And it would take about 10-ish months. That being said, the human body requires about an average of 2,300 calories a day to produce a suitable amount of energy. And to achieve this, astronauts should bring food high in fat for maximum caloric intake without eating too much and being able to kind of keep some food for the long trip. That's it.
During the CSP project, we built a water bottle rocket, which allowed me to calculate the amount of energy that was being lost and the total amount of force that was being applied. We recorded a video. We recorded launching the water bottle to get an estimated height, so that we can be able to find the kinetic energy. In order to find the total amount of energy that's being lost, we had to calculate for velocity first. We estimated around 17 feet for the displacement of the rocket, and then we got that in 1.5 seconds. This gives our total to 11.33. And then we find the initial kinetic before the launch, and then after the height right here. And then we have to find the difference between these two to find the amount of energy that's been lost. At the start, we had 80. At the start, the formula is 1/2 times the mass times the velocity squared. Our mass, we calculated to be around 80 grams. So it'll be 1/2 80, 1133 squared, which gives us 5,097.404 joules. And then for our final kinetic energy, the amount of velocity that was being used is gone, so our force is 0, which just gives us this total. Then we find the potential energy, gravitational energy that was being used, times the mass, gravity, and then displacement. We converted this to meters, which gave us this answer, and then we just add these two up for a total amount of 5,435.52 joules. We can also use a force body diagram to figure out the net force. Here, this is our rocket. F push just means the rocket went up, and then force of gravity pulling down. To calculate this, we have to do mass times acceleration, and to find acceleration, we do the change of velocity over the change of time, which is 11.33 and 1.5. It gives us 7.55 meters per second squared. Then we plug this into this using 80 as our mass, and we get a total AF of 604 newtons. Then we also find the force of gravity, which is mass times gravity, which is 80 times 9.81, which gives us 784.8 newtons. We subtract these two, and we get negative 180.8 newtons. The negative sign just means that the net force, is acting on the opposite direction of this, which is expected since gravity is opposes the rocket that's going upwards. And this gives us, in total energy loss, 5,435.52 joules and a net force of negative 480.8 newtons.
Overall, we all agreed that our project went really well. We were really happy with the results achieved through both our experiments, and we were able to make some outstanding discoveries and connections between all four sciences, even though surface level they seem very different. The CSP was really successful, and we enjoyed the process.
Wait, face to the door. Face to the door.